I don't know if any of you have seen a diagram like this. It was very, very popular about 3 years ago. In 2012, at a place called the Large Hadron Collider. Okay, Large Hadron Collider. Large, you know what large means. Collide means, bang stuff together. And a hadron is a particular kind of particle. Okay, protons, for instance, if I recall correctly, are a kind of hadron. Right? Now, what this diagram illustrates is what happens when two hadrons collide at 99.99999. I actually can't remember how many nines it is. It's a lot of nines. % of the speed of light. Okay. Objects with mass, like protons, cannot actually travel at the speed of light. Only particles without mass can travel like that, like photons, hence light. But at this incredible speed, which is more or less the speed of light, the speed limit of the universe, these two particles are racing around this enormous circuit. That's why it's called large, right? In fact, I'll just really quickly find you a picture. If you squint, right? So this is an aerial view, obviously, and you can see how far zoomed out we are because there are, there's these tiny little dots here, which are all like, towns and cities and so on. And you can see there's this huge circuit around here. It's underground, okay? And around that circuit, there are these enormous magnets powered by incredible amounts of electricity, which just blow the mind, that around here are accelerating, just like cars around a racetrack, are accelerating particles around and around and around until they go at this insane speed, and then they collide and they do this, okay? Now, why build this multi-billion-dollar project, which took many, many years to create, many man-hours, to do this? Well, what was the purpose, okay? And the answer was, they were searching for something. They were searching for something. You might have heard of this. Again, it's because back in 2012, they discovered this particle, and we'll get to what discovery means in a second. They were looking for this thing called the Higgs boson, okay? Just like hadrons, bosons are a kind of particle, okay? And Peter Higgs, I believe it was a physicist who theorized the existence of a particular kind of particle. You guys know about protons and neutrons and electrons. You might have heard of quarks, up and down, and strange and charm, and all those kinds of things, right? The Higgs boson was one of the particles in the standard model of physics. And here's the interesting thing, right? We think, again, we're referring back to what we were saying before, we think of science as an observing sort of thing, right? You observe something, you experiment, you repeat, and then you'll see some patterns. And that is exactly what it is, okay? The vast majority of the standard model of physics, like protons and neutrons and electrons, we know about because we have observed them, right? Like we designed incredible, microscopes and instruments that allowed us, through scientific principles, to observe most of the particles here, okay? But here's the mind-blowing thing, right? What happened was, when they put together this model, right, it's a mathematical model. And so therefore, in the same way that, say, like a mathematical equation, right? If I gave you an equation like this, you guys know enough maths to know that there are two solutions to this equation, right? The two solutions are x equals 3 and x equals -3. Okay, you could put either of those numbers in and you'll get a solution to the equation. Okay, now this is a very vastly oversimplified way of illustrating to you that in the standard model of physics, there are equations that govern what is going on and how the particles interact with each other. Okay, but the equations that govern them draw you to certain conclusions. For instance, they draw you to the conclusion that, I should have two solutions to this, right? The standard model of physics predicts a certain number of particles, including this guy, right? Now, it predicts it mathematically, but it's never been observed. The reason it's never been observed is because you need this enormous apparatus, the Large Hadron Collider, in order to create the conditions that could possibly make one of these actually observable to us, okay? In the same way that the wavelength of light actually has a size. So therefore, there's a physical limit to the size of objects that you can see just by using photons, okay? By using, an eye, no matter how powerful your microscope is. So therefore, we design microscopes that do not use photons, they do not use light, they use electrons. And so we call them I think we call them scanning electron microscopes, right? Instead of bouncing light off an object, they bounce electrons off. And that's how we can see much, much smaller objects, okay? In exactly the same way, the Large Hadron Collider was built based on a mathematical expectation that something exists that we have never ever observed, right? Billions of dollars and many, many years of work went into creating this thing because of a mathematical prediction, right? So mathematics has led the way for science to then confirm this, right? There did have to be, millions and millions and millions of these collisions happening every second of every day for many months in order to confirm that this particle actually did exist, okay? But that's another mathematical story which I'll save for another day, okay? So I guess my point, my conclusion, right, is that if we come back here, this idea that there are different ways of knowing, there are different ways of coming into knowledge and being sure of what we know, right? They all need to be complementary. But they relate to each other in different ways. And that's why I say that when you think about why is mathematics in STEM, okay? It's because mathematics pioneers the way, in so many examples, for science to say, okay, what should we test? It's not the only pioneer, but it is one which has led the way in a variety of examples, and I hope I've demonstrated that to you this morning.